Hello and welcome to a video on osmosis. Today we're going to be going through different examples of how the movement of water affects plant cells that I've got in green and animal cells that I've got in red here. We'll start by defining what osmosis is. It is the passage of water molecules down the water potential gradient, so from high to low. Water potential gradient, and water potential is, I'm just going to draw it in like that sign there, like that. Yeah, and it's across a partially permeable membrane. Which means it only lets certain things through. So we can see here, I've tried to represent these purpley dots as the water molecules and these green dots as like solute molecules. So we can tell that because there's a higher concentration of solute at this side, but because here where there's not as many solutes, there's going to be more opportunities for there to be water molecules. So we've got a higher concentration of water molecules on this side, and a lower concentration of the water molecules on this side. So net movement of water by osmosis is going to be in this direction. So we know that water potential is the measure of the tendency of water molecules to diffuse from one region to another. So if we had a high water potential, then there'd be like a big kind of difference. So the pure water has the highest water potential, and that is 0 kPa, and the lower water potentials go in minus numbers. So in mine, it might be minus 10, or it might go even further to like minus 500. It just depends. So if we had pure water, there'd be no solute dissolved in that. So if I just drew here, we'd have absolutely no solute, so it'd be all water. So there'd obviously be a very high chance that the water would move to this area because there's a lot more there. If there was if we pretend these dots here are the solute instead, there's going to be less room for the water, but there'd be more route this way, so it would go the other way. Again, we remember that water will move in both directions, so it won't just go this way, it will go that way as well, but the overall net movement would be more this way. So when we're talking about net movement, so which is like the overall movement. So when solute molecules are added, they lower the water potential of the solution, and so the more solute molecules in the solution, the lower the water potential. If the water potential on both sides of the membrane becomes equal, there will be no osmosis, but the water molecules will continue to move randomly. So that is called an isotonic solution. So this is when they're like at equilibrium. And then we can have a look at we know the water potential of the cells. Say if this here, in this case, is just the surrounding fluid in this box here. If this is pure water, then that's going to be a very high water potential. So it's going to be high water potential. So that means there's going to be lots and lots of water molecules outside of the cells. And there's going to be some water molecules inside the cells, but not as much as outside. So the net movement is going to be to go into the cells by osmosis down the water potential gradient. And what happens with the animal cell is that it gets that much water in it that it bursts, as we can see here. It's burst, and we call that it's become cytolized. However, the plant cell, we can see that it's just become more swelled because the membrane's pushing against the cell wall, but because the cell wall is very strong, it's not going to break and burst like the animal cell, but it is going to become what we call turgid. So it's quite swollen. And then if we're looking at here in contrast, so if we had a concentrated sugar solution, so if we had, I'm going to say that move it in a different colour, if we had lots of sugar outside, then we'd have less room for our water, so we wouldn't have as many water molecules outside. But we might have a lot more water inside than compared to outside. So the water's going to leave the cells, move out the cells by osmosis down the water potential gradient again. And this time what is going to happen is the plant cell membrane, instead of swelling, it's going to pull away from the cell wall as water leaves the cell, as we can see here, and then that is what we call it's a cell becoming plasmalized. And that is, it's sometimes described as flaccid. And that can be when a plant might become wilted. And then if we look at the animal cell here, what's happened here is that the cell has shrinked and it appears wrinkled, and it is called crenated. And this is because of the movement of water in and out of the cells. Because of the water potential gradients. And we can say that when we're describing these kind of solutions, we've said that if they're equal on either sides, it's isotonic, but if we have a high water potential, it's hypertonic, and if we've got a low water potential with lots of solute, it's a hypertonic solution. Okay, and then see if there's any more keywords, and I believe that is everything for this video. Thank you for watching.